I welcome you all for this lecture series on artificial intelligence and machine learning. In this lecture, we will discuss the topic gradient descent optimization. In that, one type of gradient descent optimization, namely stochastic gradient descent. First, we should know why we should learn this gradient descent optimization. Gradient descent is a fundamental optimization algorithm in machine learning that iteratively adjusts model parameters to minimize the loss function. Studying gradient descent helps in understanding how models learn from data and converge to optimal solutions. It is essential for training neural networks and other machine learning models. Mastering gradient descent enables effective model optimization and improved performances. We'll see one by one. First, introduction to gradient descent. Gradient descent is a fundamental optimization algorithm used to train neural networks. It operates by adjusting the model parameters, namely weights and biases, so that the model prediction becomes more accurate. The adjustments are made in the direction that reduces the value of loss function, which measures how far the predicted output, or that is y, output y, is from actual output y. By computing the gradient, the partial derivatives of the loss function with respect to each parameter, and moving in the opposite direction of gradient, the algorithm gradually improves the model's performance. Before going into the topic, let us know the overview of the neural network. All you know that the neural network consists of input layer, one or more hidden layers, and output layers. Each neuron has a connected by weights. That means each input is associated with the weight value. This we have seen it in the previous lecture. Suppose the neural networks are connected like this. This is my hidden layer. This is my output layer. Each neuron is this is input patterns, and each neuron is connected with one weight value, and bias we have b1, b2 like this, and here output is been connected like this. So each neuron applies a weighted sum followed by an activation function. After applying, each neuron is calculated here x1 w1 plus and also we'll write it as x2 W2. Similarly, for this neuron plus B2, this we can call it as the weighted sum. After finding out the weighted sum xi, wi, we will be applying this into the activation function. This is the basic overview of the neural network. And we have forward propagation. That means, suppose we have one hidden layer, inputs we are applying x1 and x2, and the hidden layer of HJ, any H1 or H2 or HD, the output neuron, the Y cap, we are calling it as the prediction. That prediction only we are going to calculate it with that is compared with the targeted output. The targeted output is not matching with the prediction. We are going to calculate the error function. We are sending back and forth until we get the zero error. Will be doing that process and calculating the hidden layer outputs. Each hidden layer, we are finding out the output like this xi, wi, xi, wij, and xi plus bj. After this is the weighted sum, and here applying the activation function, we'll take the sigmoidal function hc is equal to phi of the output of the hidden layer hj, sigma of zj is equal to 1 divided by this value. We are going to substitute it, and calculating the output layer. Once after finding out the value, we are going to find out the value for prediction value for the output layer also. Output prediction will be like this. This y cap represents the predicted output. This only we are going to compare with the targeted output. So if it is not matching this error, we are going to calculate. My targeted output is y is equal to 1. My y cap is equal to 0.7. What is the error? 1 minus zero point 0.7 is the error, zero point 0.3. So till we get 1 minus 1, we are going to repeat the process that we are calling it as the epoch. For that only we are going to apply the loss function. So it measures the loss function. This is given by minus y of this is the targeted output. This is the predicted value 1 minus y minus of y into log y gap plus 1 minus y into log of 1 minus. This is the loss function we'll discuss. So the loss function is given by function measures prediction error. The loss function quantifies how well or poorly a model is performing during training. For binary classification tasks, the most commonly used loss function is binary class. Most commonly used loss function is binary cross entropy. It is defined as L is equal to minus of y into log y gap plus y 1 minus y into log of 1 minus y gap. And the function analyzes incorrect predictions heavily, especially when the predicted probability diverges significantly from the true class. Minimizing this function via gradient descent enables the model to make increasingly accurate predictions. Next, the step-by-step overview of the training. The neural network training involves several key steps. In forward propagation, the model computes the predicted output, that is y cap, by applying activation functions to the weighted sum of inputs. Then the loss function calculated the error between predicted and actual outputs. In the back propagation, that is backward propagation step, gradients of the loss with respect to each weight, that is dl by dw, dlw, db, biases each weight and bias are computed. Using these gradients, weights and biases are updated, and the updation is given by w is equal to w minus old weight. This is the new weight. The old weight minus eta into dou L by dou W. This dou represents what? The learning rate. This we are going to fix it. And where eta is the learning rate, this process is repeated across many epochs until the model converges to a solution with minimal loss. Next, the types of gradient descent. There are various types are available. Gradient descent has three main variants in batch, stochastic gradient, and mini batch gradient. In batch gradient, the entire data is used to compute the gradient in each iteration, leading to stable but slow updates. In stochastic gradient, the second type, SGD, stochastic gradient descent, weights are updated for every single data point, making it faster and suitable for large data sets, though it introduces noisy updates. And mini batch gradient descent strikes a balance by using small batches of data, example 32 or 64 example samples, allowing faster convergence with moderate stability. Choosing the right type depends on the dataset size and the computational resources. Next is stochastic gradient descent, SGD. SGD updates the model parameters after each individual training sample instead of after processing the entire dataset. This allows for quicker updates and make it ideal for large scale data. Although updates are more erratic and may not always move directly toward the global minimum, this randomness can be beneficial. It helps the algorithm jump out of local minima and saddle points, large data set. Because each step is based on a different sample, as GD introduces variability, but it still converges efficiently with the proper tuning of learning rate and iterations. Next, the examples of SGD in stochastic gradient descent interaction. Consider an input x1, x2, etc. And two inputs I am going to take with the true outputs y. and the neural network computes the predicted output using the sigmoidal activation function after finding out the weighted sum. After applying the sigmoidal function, we are finding out the predicted output using sigmoidal activation function, where z is equal to w1 x1 plus w2 x2 plus b. After computing the loss, we determine gradient dou L by dou W1, dou L by dou W2, dou L by dou B. Okay. We are going to find out the gradients. We determine the gradients, these values. The gradients are then used to update the parameters W1 equal to W1. This is the new old weight. This is the new weight. Eta into dou L by dou W etc. W1, W2, etc. And similarly for W2, W3 and B, these updates are repeated for each sample, progressively improving the model's accuracy. Next, visualization and loss versus epochs. As a training progress, we expect the first point. We expect the loss to decrease steadily. In batch gradient descent, the loss curve is smooth because the updates are based on the whole data set. In contrast, SGD introduces a jagged, noisy pattern to the loss curve due to the frequent updates using single samples. However, despite this noisiness, SGD often reaches a good solution faster than full batch methods. Selecting appropriate learning rate, that is eta is the learning rate, is critical. Too high may cause divergence, while too low may slow convergence significantly. So we cannot choose either too high and too low. So too high may cause the too, if the eta value is too high, what it will do is it may cause the divergence. If this value is too low, that is slow, otherwise too low, slow, it convergence significantly. Divergence, convergence. Okay. Next, benefits of SGD. SGD offers several advantages, particularly when working with large data sets. It allows for faster updates and require less memory since only one example is processed at a time. The randomness in SGD helps avoid local minima and find more general solutions. It is well suited for online learning where the model needs to be updated in real time and as new data arrives. Overall, SGD provides a good trade off between speed, performance, and scalability, especially when improved with modern techniques. Next, challenges in SGD. While SGD is efficient, it also comes with the challenges. The frequent updates based on individual samples can lead to high variance in the gradient estimates, resulting in unstable convergence. Unstable convergence. This is main challenge of this SGD. The frequent updates based on individual samples can lead to high variance in the gradient estimates, resulting in unstable uh, convergence. It is also highly sensitive to the choice of learning rate. A poor choice can also model the diverse or get stuck in non-optimal regions. Additionally, SGD may oscillate near the minimum and never fully settled, which can impact the final model accuracy unless improvement applied. Next, common improvements to SGD. The overcome the instability of SGD, several techniques are used. Momentums add momentum. This is very important property in this. Momentum adds a fraction of the previous update to the current one, smoothing out oscillations and speeding of convergence. It is defined as V is equal to beta V plus eta into dou L by tau W. This learning rate scheduling gradually reduces the learning rate during training and allowing the model to settle more smoothly near the optimal. Adam. This Adam represents Adam optimizer, adaptive. Adam means adaptive moment estimation. This Adam adaptive moment estimation combines the momentum and adaptive learning rates to offer efficient and robust convergence and is widely used in training deep learning models. So once if it has been stuck, we have to use this model to overcome or to improve the SGD, stochastic gradient. Hope everyone understood about the concepts of a stochastic gradient algorithm. The remaining things we'll discuss in the next lecture. Thank you.